Hello students, I welcome you in today's session of physics, and in physics I am going to present you the chapter number 15, which is your flow of liquids. You can see here this is your chapter flow of liquids. First we will look at a syllabus what we have to study in this chapter. So you can see here first we have to take the viscosity. After that, Stokes' law, terminal velocity, streamline and turbulent flow, critical velocity, Bernoulli's theorem and its application. Clear? So these are the things which we have to cover out in this chapter. This is your syllabus. Clear? So first we will discuss about this ideal liquid. You can see here this is the first topic. So an ideal liquid is one which has the following two properties. You can see there which liquid you can say an ideal liquid. So first one you can see the zero compressibility. An ideal liquid is incompressible, that is on pressing the liquid there is no change in its volume. Fine? Or you can say that there is no change in its density. So most of the liquid may be considered approximately incompressible. Clear? Because on pressing them the change in their volume is negligible. For example, on pressing water by 1 atmospheric pressure, its volume changes to how much? Only a fraction of this much. So first property is the zero compressibility. This is the one. I hope you understand it. Now come to the second one, zero viscosity. An ideal liquid is non-viscous, that is when there is a relative motion between the layers. Now first before going to start what is zero viscosity, I would like to tell you what is viscosity. Viscosity is nothing but the relative motion between the different layers of water or whatever the medium is. Clear? So an ideal liquid is non-viscous when there is a relative motion between different layers of liquid and there is no change in the tangential forces in between the layer. So in actual practice, however, there is some viscosity in all, whether it is a liquid, gas. So it is less in gases, this is important one, but larger in liquid. Means the viscosity is very much larger in liquids. Fine. Now come to the second one. This is your streamline flow or laminar flow. Here you can see here this is the topic. So what is streamline flow? So when a liquid flows such that each particles passing at a certain point follows the same path as the preceding particle, means the other particles retraces its former particle. Clear? So which pass the same point, the flow is said to be streamlined and the path is called the streamline flow. Clear? I hope you understand it. Now see here, you can see here there is a tangential velocity given in this figure, this one. So the important property of a streamline is that the velocity of the liquid can be different at different points of the streamline, but at a particular point the velocity remains constant. Clear? Here you can see that in the figure A, B, C are the 3 points on the same streamline of a flowing liquid. This is the tangential velocity V1 and this is the tangential velocity V2. And after that, after a certain time, the velocity at the point C comes out to be V3. Fine. So all those particles of the liquid which pass through A also pass through B and C. So the velocities of the liquid at these points are V1, V2 and V3. That is different. But at one and the same point such as A, the velocity is always V1. Whichever the particle of the liquid at this point, the same is true for B and C also. Fine. Now come to the streamline tube. What is the streamline tube? Here you can see that this is the figure of the streamline tube. So if we imagine a tube made up of large number of streamlines, then this imaginary tube is called as streamline. Here you can see that the figure number 2 shows the streamline tube X and Y. The boundary walls of the streamline tube are everywhere parallel in the direction of the flow of liquid. You can see here the boundaries are parallel. Therefore, the liquid can neither go out nor come through the walls of the tube. So the liquid that enter at one end X leave the other end Y as if it were flowing through an actual tube. I hope you understand. This is the important one. What is turbulent flow? Clear? This one, the third topic, which is your turbulent flow. What happened in this turbulent flow? In this type of flow, the particle of the liquids follow independent paths. Here you can see this is the streamline flow figure, such as intermingling of the two or more layers that takes place. So in this case, the velocity of the particle at a point is time dependent and the velocity gradient is not constant. Now come to the fourth one. What is the critical velocity of a liquid, or Reynolds number? This is also the important topic. So pay attention, students. When a liquid flow in a tube, you know very well the viscous forces opposes the flow of liquid. Means the layer below the upper layer, or the below layer opposes the motion of the upper layers. Fine. That is the viscous force come into play. So hence a pressure difference is applied between the ends of the tube, which maintain the flow of liquids. So if all the particles of the liquid passing through a particular point in the tube move along the same path, the flow of the liquid is called the streamline flow. This is the definition of the streamline flow. What you have to know very well: if all the particles of the liquid pass through the particular point in the tube move along the same path, then you can say that the flow of liquid is the streamline flow. This occurs when the velocity of the flow of liquids is below a certain limiting value, which is known as the critical velocity. So these are the two important definitions kept in mind. When the velocity of the flow of exceeds the critical velocity, the flow is no longer the streamline but becomes turbulent. Clear? So when your velocity exceeds the critical velocity limit, in that case the flow of the liquid comes out to be turbulent. Thus, the critical velocity of a liquid is that maximum velocity up to which its flow remains streamlined, while beyond which flow becomes turbulent. Now, Reynolds proved that the critical velocity for a liquid following in a tube is given by, this is the relation between the critical velocity coefficient, this is, you can see there, neta is the coefficient of viscosity, rho is the density, fine, and d is the diameter of the tube through which the liquid is flowing on. Here you can see that these are the terms used in this expression. Rho is the density, neta is the viscosity of the liquid, d is the diameter of the tube, and k is your Reynolds number. Fine. Now there is a note given here, so kindly read this note. Fine. So what are the conditions? Here are some conditions given here. Now I am moving to the viscosity. This is the most important topic of this chapter, viscosity. You can see here, when a solid body slides over another solid body, a friction force begins to act between them. You know very well in solids there is a friction force when the motion, which opposes the motion. Now what happened with the gases and the liquids? So this force opposes the relative motion of the bodies. Similarly, when a layer of a liquid slides over another layer, the same liquid's friction force acts between them, which opposes the relative motion between the layers. This force is called the internal frictional forces. You can see here from this figure, this one, what's going on here. Suppose a liquid is flowing in a streamline motion on a fixed horizontal surface AB. This is the figure number 4. This one. Clear? So the layer of the liquid which is in contact with the surface is at rest, while the velocity of the other layers increases with the distance from the fixed surfaces. Fine? So in the figure 4, the length of the arrows represent the increasing velocity of the layers. Thus there is a relative motion between the adjacent layers of the liquid. Let us consider 3 parallel layers. You can see from the figure A, B and C. Their velocity are in the increasing order. The layers A tend to retard the layer B, while tend to retard C. Thus each layer tend to decrease the velocities of the layer above it. Similarly, each layer tend to increase the velocity of the layers below it. So this means that in between the two layers of the liquid, internal tangential forces act which try to destruct the relative motion between the layers. Fine? So these forces are called the viscous forces. This is the important thing. So the flow of liquids is to be maintained. An external force must be applied to overcome the dragging viscous force. In the absence of external forces, the viscous force would soon bring the liquid to rest. So the property of the liquid by virtue of which, this is the definition of the viscosity, kindly pay attention. The property of the liquid by virtue of which it opposes the relative motion between the adjacent layers is known as viscosity. Fine? Now here you can see there are the few properties of the viscosity you have seen in the above example. What are these properties? The first property is a steroid liquid when left come to rest on account of viscosity. Clear? Thicker liquid, honey, coal tar, glycerin, etc. have larger viscosity than the thinner ones like water. If we pour a coal tar and the water on a table, the coal tar will stop soon while the water will flow up to a quite large distance. This is because of that relative motion between the layers. Second one, if we pour water and honey in a separate funnels, water comes out readily from the holes in the funnel, while honey takes enough time to do so. This is because honey is much more viscous than water, as honey tends to flow down under gravity. So the relative motion between its layers is opposed strongly. The third one is we can walk fast in air but not in water. The reason is again viscosity, which is very small for air but comparatively much larger for the water. Come to the fourth one. The cloud particles fall down very slowly because of the viscosity of air and hence appears floating in the sky. So here you can see the finally viscosity come into play only when there is a relative motion between the layers of the same material. This is why does not act in solid. Fine. Now you can see here what is the velocity gradient and the coefficient of viscosity. This is the topic number 6. You can see here this one. Suppose a liquid is flowing in a streamline motion on a horizontal surface OX. You can see that this is the horizontal surface and liquid is flowing in this direction, figure number A. The liquid layer in contact with the surface is at rest while the velocities of the other layer increases with increasing distance from the surface OX. The highest layer flow with maximum velocity. The upper one you can see there, its velocity is Vx plus delta Vx and the velocity of the below layer is delta Vx. So let us consider two parallel layers PQ and RS at a distance of Z and Z plus delta X from OX and Vx plus delta X with their velocities in the direction of OX. You can see from the figure number 8. Thus the change in the velocity in a perpendicular distance delta Z is how much? Delta Vx, that is the rate of change of velocity with distance perpendicular to the direction of flow, that is delta Vx by delta Z is called the velocity gradient. This is the definition of the velocity gradient. How can you define it? The rate of change of velocity with the distance perpendicular to the direction of flow, it's called its velocity gradient. Now what the unit of velocity gradient is per second. This is the unit and the dimension is t to the power minus 1. I hope you understand it. Now you come to the figure number B. Let us consider a liquid layer of A, area of class A, whose area is capital A, at a height Z above the OX. So the layer of the liquids immediately above it tend to accelerate with tangential viscous force F, while the layer immediately below it tend to retard it backward with the same tangential. Here you can see that two forces are acting in equal and opposite direction. One is directed in this direction and one is in opposite direction. Clear? So the same tangential force F according to the Newton's viscous force acting between the two layers of a liquid flowing in the streamline motion depend upon the two factors. Now what are the two factors? You can see here these are the two factors. These one. First one says that it is directly proportional to the contact area A of the layer. You can say that force is proportional to area, and the second one, it is directly proportional to the velocity gradient between the layers. So if you combine both these terms, finally the force is proportional to Vx by delta Z, or you can write it like this. Clear? If we introduce the sign of proportionality where neta is the coefficient of viscosity, so the formula comes out to be F is equals to plus minus Na delta Vx by delta Z. Now why we take here plus minus? Because the direction of the below layer relative motion between the upper and the below layers, it might be in the opposite direction. You can see here what is neta? Neta is the coefficient of viscosity of the liquid. So if we in this formula, in this one, if we put A is equals to 1, so what we get here? Delta Vx by delta Z is equals to 1. In that case, the force and the coefficient of viscosity is almost equal. So we can say that the coefficient of viscosity of a liquid is defined as the viscous force per unit area of contact between the two layers having unit velocity gradient between them. Clear? Now if we talk about the dimensions and the unit of coefficient of viscosity, so this is the dimension and the unit is, you can say that we measure the viscosity in poise, or you can say that 1 kg per meter per second. Clear? I hope it is understood, you understand it. I am leaving this topic, important points regarding the, you read it by yourself, what are the effect of pressure, density and the temperature over the viscosity. If you have any doubt, kindly ask me in the comment section. These are the some few points. Now come to the Stokes law. This is the our next topic, and we will discuss this effective force on a body falling in a liquid, which is your Stokes law, in our next lecture, lecture number 2. Clear? Till that, students, do study. Thank you class. Thank you very much.